We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello everyone, myself Professor Rutul Mahajan from SNPITRC Umrag. Today I'm going to talk about push-down automata, Unit 4 in Theory of Computation. Now before going to why we need push-down automata, let's quickly see the basis of that using this Chomsky hierarchy of grammars. There are 4 types of grammar, type 0, type 1, 2 and 3. Here in this Venn diagram, we can see that type 3 grammar is regular grammar, type 2 is context-free grammar, type 1 is context-sensitive grammar, and type 0 is unrestricted grammar. Now we can see the machines which can simulate this kind of grammar and languages. The languages which can be generated using regular grammar can be accepted by finite automata. Means regular languages, to process the regular languages, there are the machines which are called finite automata. Now to process the context-free grammars and context-free languages, there is a machine called push-down automata. So we are going to work over here the type 2 languages and type 2 grammars in this unit, that is context-free grammar and context-free languages. Type 1, that is context-sensitive grammar, which can be accepted by linear bounded automata, and type 0 is the unrestricted grammar that can be recognized using Turing machine. Now the main thing to explain this Chomsky hierarchy is that to explain the thing that type 0 is the most powerful grammar. We can see from this diagram, or we can say Turing machine is the most powerful machine which can accept or recognize unrestricted grammar or context sensitive grammar or context free grammar or regular grammar. Means we can say that any language which can be accepted by finite automata, that can be definitely accepted using Turing machine. So same thing we can say about the push-down automata is that the languages which can be accepted by finite automata can also be accepted using push-down automata. So the thing is that push-down automata is more powerful version or more powerful than finite automata. Let's see how. The need of push-down automata. FA is for regular languages, as we seen in the previous Chomsky hierarchy. It can remember the finite amount of information. Push-down automata is a finite automata plus extra memory. Means it is something extra with finite automata. That is extra memory, that is called stack. It can remember infinite amount of information. PDA is for contextual languages generated by CFG. So in short, what we can say, PDA is NFA null plus a stack. And stack is assumed to be unbounded, means with infinite memory. So using this combination, we can simulate any kind of contextual languages, and we can say that whether the string we have passed is accept or rejected. Push-down automata can be defined as T is equal to Q sigma gamma delta Q0 Z0 and F, where Q is the finite set of states. Over here means these things are same as finite automata, means Q is the finite number of set of states, sigma is the input alphabet, Q0 which is in Q means set in the set of states, initial state, then F is a final state, and delta is a transition function. Okay, these are the things which are as it we have studied in finite automata. Transition function is bit different than the finite automata. We will see that. The new symbols are that gamma, that is an alphabet. This is called an alphabet called stack alphabet or stack symbol. Means we have introduced stack in the push down automata. So whatever symbols we have added to the stack or popped from the stack are represented using gamma, that is stack symbols. Z0 is in gamma is a particular stack symbol called stack top symbol. It's over here. And delta is a transition function. Now, how we will define the transition function? First, transition means we have to transit from one state to another state. So what will be the input? One of the entity in input is state, Q. Okay, any state from set of states, that is Q. And upon giving that transition function, what we are getting as output? Another state. So there will be Q. Okay, so this is input and this is output. Another thing what we have to give as a input, that is input symbol alphabet, input alphabet, that we read from this tape, from this tape. Okay, and apart from that, stack symbols are read, that is gamma in the input. Upon giving this input, that is set of state, state from set of states, input symbol and stack symbol. Then we will get new state and new stack symbol that as a output. This is what our transition function looks like in PDA. Let's see here. This can be the tape can be visualized like this. In this, we will see how PDA works. The tape is divided into infinitely many cells. Each cell contains a symbol in an alphabet set sigma. Okay, then which is same as finite state automata. Then tape head moves in a one direction, scans at a cell on tape and can read a symbol on the cell. In each move, head can move to the right cell. Stack head always scans the top of the symbols in the stack. It performs two basic operations, push and pop. Push means adding a new symbol at the top. Pop means reading and remove the top symbol. Alphabet of stack symbols are represented using gamma, that we have seen in that definition. Now, how we interpret this moves in the push down automata. Delta QAV is equal to PU. What does it mean? If tape head reads A, the stack head reads V, top symbol V, and the finite control is in a state Q, then one of the possible move is that next state P, next state is P, this one, next state is P, stack top symbol V is replaced with U at stack, and tape head moves in a right direction, one cell right. This is how this delta QAV PU move can be interpreted. Now let's see different kinds of stack operations with transition function. Delta Q null V is equal to PV, means null transition. Upon giving null input, we are moving to the next state, from Q state to the P state, and also we are changing the stack. Sorry, we are not changing the stack symbols. The important thing is that without giving any input, means with null move, we are changing the state. Then push operation. Delta QA null PU means over here we can see that there is nothing in the stack, top of the stack, and we are pushing U onto the stack. And apart from that, state is also changing. That depends. The important thing to concentrate over here is that on state Q, upon giving input A, we are pushing U onto the stack and changing the state to the P. This shows the push operations. Means from empty stack to we are entering U on the stack. Now let's see the pop operation. Delta QAV is equal to P null means that pop operation. How? Let's see. Upon reading the symbol A while in a state Q, and when stack top contains V, we are moving to the state P, one cell ahead, right side, and popping out the symbol V. This is what we call a pop operation in PDA. Now, during design of PDA, we have to keep these two things in mind. This two way we can design a PDA. Designing PDAs those accept by final states, and designing the PDAs those accept by empty state. Now, the question is that acceptance by final state, what we need to check whether input is exhausted, means input string on the tape is finished or not, and on finish of completion of input, our PDA is on in a final state or not. If it is in a final state, input is also exhausted, then we can say that it is accepted. This is the criteria for acceptance by final state. Now, acceptance by empty stack, we are also another entity in the push down automata, that is stack. So we can check that also. Using that also we can check whether our input is accepted or not. So what is the checklist for this? Input is exhausted, means input is finished or not on the tape. And on the completion of input, is there any stack symbol remaining on the stack, or it is empty? Means we need to have empty stack, while we have to check by empty stack. Means we have to check the acceptance by empty stack, then we need input exhausted and empty stack. So the question is that, does the PDA that accepts by empty stack need any final state specified in the design? This is the question to worth thinking. Do we need any accepting state? How we come to know that particular input is accepted? Do you think we need it? Yes, we need it. Means we need to show on particular state if our particular input, on our particular input stack is empty, then we can say that it is accepted. Now let's see it by example. Construct a PDA accepting language WR. That is, W is one word and WR is the reverse of that word. Means in the simple words, if I can say, this is the language of palindromes. If I talk about WW raised to R as 0 plus 1 whole star, where W comes from 0 plus 1 whole star, means it is a combination of 0 and 1. Then W raised to R is just a reverse sequence of W. So CFG for a language of WWR can be written as S produces 0 as 0, means starts with 0, ends with 0. 1 as 1, starts with 1, ends with 1. And terminal symbol null, means either my language can start with 1 or it can start with 0 and terminated with null. Any combination of this can be made. Means the important thing is that starting and ending symbol are same. That is how we can define any palindrome language. So for that, PDA can be defined as this. This is our answer. But let's see how this answer comes. Now, first, these are the steps or transitions. How from using that, I get the acceptance or rejectance of any particular string. These are the possibilities. If I on state Q0, first state, and there are two possibilities. My input can start with 0 or it can start with 1. Then again, my stack can be empty. So top symbol is Z0. So when my state is Q0, then if input is 0, what I need to do? I need to just push it onto the stack. The logic is that whenever till midpoint, just push the symbols whichever come on the input tape. After that midpoint, just pop that symbols and match it with the input symbol. If the symbols in the stack that we have pushed earlier for the first half is matched with the symbols which are currently occurring on the tape, then we can say that we are going towards acceptance. So let's see that. Q0, 0, Z0, then we have to push. 1, Z0, then we have to push. Now, if stack contains 0 or 1, okay, so in that case also, if any of the symbols 0 or 1 came, I need to just push it onto the stack. Means grow the stack by pushing new symbols on top of old part. Now over here, using this transition rules, we can process the W part. Now it comes the W raised to R reverse part. So before that, we need to switch to the pop mode. How we will switch? Using null transition. We are not reading any input symbol. So if stack contains 0, there are three possibilities. Stack contains 0, 1 or Z0. We just have to switch. We don't have to do anything. We just have to change the state from Q0, this Q0 to Q1. Okay, in any case. So now we have switched from push mode to the pop mode. Now what we are doing, if we read the input 0, on Q1 state, if we read the input 0 and my stack contains 0, see over here, input is 0, stack contains 0. Then what I have to do, I have to pop that symbol, this symbol from stack, I have to pop. Both are matching, so I have to pop. Same for Q1. On Q1 state, if input is 1 and if stack contains 1, then just simply pop that symbol. Similarly, do these things till we exhaust the input. Means if I get null in the input, means my string is finished. At that time, if my stack is also empty, that is Z0, then I can say that I will move to the acceptance state Q0 with no operation on stack. That is just the acceptance state. This is how a particular palindrome string can be processed using pushdown automata. So at the last, what I have to write? State of set of states Q, that is Q1, Q0, Q1 and Q2. Over here you can see three states, Q0, then Q1 and Q2 are used. Okay, so set of states Q is equal to Q0, Q1, Q2. Alphabet symbols I have used is 0, 1 and null. 0 and 1. Here over here I have mentioned star, so 0 and 1. Stack symbols in stack I have used 1, 0 and Z0. Transition function, we have mentioned this transition functions. Then Q0 is the initial state, Z0 is the stack symbol, and what is the final state? That is Q2. This is how my answer can be written. Now, how I have to draw the state diagram for the same transition function. Then this is my current state. Okay. Then this is my next state. Over here, I have to mention the next input symbol. This is current stack top, and what I am replacing on stack with this. This is how I have to write the state diagram. This is taken from the reference of one paper. Delta Q I A X is equal to Q J Y. Now over here, let's see it by this example of same palindrome language. This state diagram I have drawn for the same transition function. We have three states in a set of states Q0, Q1 and Q2. So first draw this three states Q0, Q1, Q2. Q2 is our acceptance state, so show it with the notations of acceptance state. Then our alphabet symbol is 0, 1, stack alphabet Z0, 0, 1, Q0, 1, Q1, Q2, like this. Now, what I have to do? First, grow the stack by pushing. Means this one, pushing. All this we have to convert to that Q0. Means on Q0, if we get input 0, we need to push 0, Z0. So let's see. 0, input is 0. Stack on stack, if it is 0, then push this 0 onto the stack. 0, Z0. If 1 on input, stack is Z0, then push 1, Z0. If 0 is input in stack, there is a 0, then push this 0 onto the stack. That will become 0, 0. If 0 is there on stack, it is 1, then push, then it will become 0, 1. On stack, on input, it is 1, stack is 0, then push this 1 onto the stack, that is 1 0. On stack input it is 1, on stack it is 1, then again push it onto the stack 1 1. Now when we need to switch to the pop mode, means at the middle of the input string, at that time I have to do the null transition, that is using input symbol null. So over here you can see there are 3 possibilities on the stack. We don't have to do anything with the stack. So when stack contains Z0, then I have to simply do nothing, null, Z0 replaced by Z0. If stack contains 0, then I have to do nothing, simply replace 0 with 0. If stack contains 1, then I have to do nothing, simply replace 1 with 1. And change to the state Q0 to Q1. Now we have switched to the pop mode. So pop this stacks for matching the symbol. If input is 0 and stack contains 0, then simply pop it. If input is 1, stack contains 1, then simply pop it. You can do this any number of times your input contains in this situation. The pop will occur. Now when your input is exhausted, that is null comes, and stack contain nothing, that is Z0, then it is the acceptance states. We have to do nothing. We have to replace Z0 with Z0 and go to the simply from state Q1 to Q2. This is how our transition diagram for palindrome in PDA can be drawn. Now same we can simulate for language, A raised to n, B raised to n, that is we can say n greater than or equal to 1, language of equal number of A's and B's. Then how we construct a PDA for this? The basic idea is that this is same as I explained in the previous example. First we have to write, for the getting idea, we can write the various strings in this languages which can be generated using this grammar. This is the grammar. If you know the grammar, just write down that grammar first. And this pattern, from this pattern you can get the logic how you can design the PDA. The idea for designing this PDA is that here every time A comes before A, means before A, then push it onto the stack. Whenever we need to count any symbols, just push that symbols on the stack and match when other symbol comes. Over here we can see that whenever A comes before A, before B, then push it onto the stacks. Okay, whenever means till completion of all the symbols that are A, just push it on the stack. When B comes, just start popping A. Means for one B, there should be one A in a stack. For another B, there should be another A in the stack. For third B, there should be another A in the stack. If there is a third B but there is no A in a stack, then we can say that it is not accepted. This is what our idea of designing a PDA. So simply we will, what we will do on the first state Q0, whenever A is coming, whatever symbols are there in the stack, we are just going to push this A onto the stack. When we are switching the state, when this symbol is changed, because we need to pop the symbols when symbol is changed. Okay, let's see in this diagram. Over here, let's see. These are the only 5 rules, transition diagram, rules. When first we will start with state Q0. Okay, now there can be how many possibilities of input? Only one. What? It should be start with A only, because it is A raised to n, B raised to n, and n greater than or equal to 1. Means the minimum the smallest string is AB. So it must start with A. It can be possible that in this stack, if it is a starting symbol, then it can be 0. If it is the intermediate symbol A, then there can be A in the stack. So when input is A, state is Q0, it is first symbol, so stack is also empty. So we just have to push it onto the stack. So this 2 symbol represents push mode. Same way when the symbol changes on Q0 state. If the symbol changes, means after A, 3 times A Z0, then push it on the stack, A Z0. Second A, then we just have to grow the stack by pushing it onto the stack. third A, then again we just have to grow the stack by pushing it onto the stack. Now first B came. Now my stack contains one A. So what I have to do, I just have to pop that A. So I have represented this A is popped from stack, and at the same time I have to switch the state because I'm currently now in the pushing mode. On the Q state, I have to switch to the pop mode. So I will change the state to Q1. Now any number of times B comes, and if it match with the A in the stack, then we just have to pop it. If our input is exhausted and stack also empty, then we have to go to the acceptance state. This is how our A raised to n, B raised to n PDA can work. Similar way, you can construct a PDA for A raised to m, B raised to m plus n, C raised to m, where m and n greater than equal to 1. The idea for this is that we can say that any number of times A comes, the same number of times B comes. Any number of time B comes, the same number of time C comes. This is how our PDA can be designed. Means how we have to count PDA in PDA. Just remember one thing: use the states for sequencing and use this stack for counting. Means first I need A. Okay, in my valid string of this grammar contain, it will start with A, then middle symbol will B, and the last symbol will C. No other sequence change will be there. So maintaining this sequence, I will use the states. Okay, now to maintain the counting, means as many times A comes, the same number of times B comes, then the remaining B's should be matched with the number of C. So how I will match this? This first m times A, I will push onto the stack. The same m times B should be there on input. If remaining B, that is n number of time B, are there, what I have to do? I have to push it onto the stack. Okay, remaining B's. Right? Now for the same B, there should be n number of times C. Means just like the previous example. The state diagram for that will be like this. These are few examples that you can practice for the better designing the PDA. Thank you.